Our next speaker is David Robbins. He is a technical writer and master in geology, and he'll be telling us about how it happens and worship.
Thank you. So I'm Dave Robbins. I'm really glad to be able to present at this ASA 2025 annual meeting. It's the fourth time I've been able to do this, and each time I learn a lot from it. So I really appreciate ASA for giving people the opportunity to do this sort of thing. Today I'm going to take in a little journey. Probably should be a little bit briefer journey, but I'll probably go a little bit over the 20-minute anyway. A journey into geological history of an area in British Columbia that's related to where we are today. So my interest in geology goes back to a kid picking up rocks along the beach or in the mountains. I remember our family coming to Colorado years ago. I went to Michigan State for my bachelor's and then pursued a master's degree at University of Calgary. And it's kind of hard to imagine that was actually 50 years ago. But it's a drop in the bucket compared to geologic time, so I feel okay about it, right? Yeah. So during my college years, this is kind of what brings me to this point today, I'd really drifted away completely from God, even though I was raised in a congregational church. When I completed my master's degree, I had a bunch of personal stuff going on that really drove me back to ask God, was he there? And turned out he was. So I wound up in northern Manitoba at Inco. Ed and I have had an Inco connection here, but mine was a total of 3 months. I worked there, was a mine geologist in a underground sulfide deposit that was metamorphosed, and so there was a fit between that environment and my master's degree. But I decided that I didn't want to be in a location for long-term up in Manitoba. So I returned to Michigan, had met Nancy in northern Manitoba, my wife, and once we started raising a family, I needed to find work to do, so I became a technical writer. We find ourselves today, obviously in Colorado, which is part of a massive chain of mountains that goes all the way through South America, almost to Antarctica. And even though the geology that I'll be describing is different than the geology we see just west of us, it's all connected. Here's some pictures from Alaska last summer just to show the range of different environments. This is a huge shield volcano. These are granitic mountain peaks. This is a lava flow from central BC. And here we have folded rocks looking across. This is called the Rocky Mountain Trench, looking at the folded structures that form the Canadian Rockies. What do we owe the mountains to? Years ago, there was a man by the name of Alfred Wegener. He was a meteorologist and geologist. And he came up with the idea that at one point, all the continents that we now see on the globe were connected together. And his theory was called continental drift. So he theorized that these continents had broken apart and were drifting around on the planet. Nobody believed it back in the 1930s. I don't believe in his lifetime he was recognized for the theory. Maybe I'm wrong about that, but it hadn't really caught on. He noticed that there were similar fossils connecting continents that were now separated. For example, South America and Africa, or Antarctica and Australia. So this is where his theory of drifting came from. And he was right. So much
later, scientists realized that the mid-oceanic ridge is in the Atlantic Ocean, which goes all the way from Antarctica up through Iceland. Iceland is the landform expression of that ridge and the volcanism that's there. That if you look at the ridge where it's spreading, you see these magnetic stripes parallel on either side. And this is evidence from the paleomagnetism of a spreading ridge. So this was proved, I think this work was done in the 60s, of continental spreading.
And it really led to the theory of plate tectonics, which today has become the unifying theory behind global geology on the Earth. So we're going to talk in a minute about BC, and I'll show you where we're going with this. But basically, as the Atlantic Ocean opened up, North America was forced to the west, and as it was forced west, different terrains that were forming out in the Pacific environments were forced up, bulldozed in a sense, onto the continental crust, which was over here. So this is a picture today showing our continental crust in North America, which extends now all the way to the Pacific Ocean out here. You still have a plate active in that area with volcanism and so forth. There was just an earthquake I think this week, a few days ago, up in the Aleutian Islands from faults caused by these kinds of plates. And over the years, different geological terrains were bulldozed onto the moving continental crust to form North America. So today, we're going to be looking at this little area right here. So this is my thesis area back in the early 1970s. Here's British Columbia, here's Alberta, Trans-Canada Highway. The Columbia River starts in this location, comes up, makes a big bend, and then comes down to the U.S. and out to Washington. So they built a dam in the 70s called Encampment Creek Dam in this location. It backed up a big reservoir river back up here. And the area that I'm going to be talking about was in this area. So the big picture here, these are the Monashee Mountains. We flew in by helicopter and established 3 different camps the summer that I was there. Actually, there was also a 4th up in Foster Creek, but these were the camps that related to the thesis work I did. So here's some pictures of the area. There's still snow covered in early July, but we walked these ridges in our mapping here and here. Here's a picture of the lake that's in the Rocky Mountain Trench. So the Mica Dam is down this direction. This would be the Rocky Mountain Trench forming here, which turns out to be a major fault system. This is one of my major professors. We actually visited him a couple of summers ago. He's in his early 80s now. Phil Simony. Worked for years, 30 years probably, in this area and surrounding areas. And really it was instrumental in determining what the structure of these mountains were. Very fine, detailed mapping that showed the relationships and folding and so forth. He was recognized by the Canadian Society of Geology, I'm sure, at one point. My other professor is not shown here. This is our field assistant, Dave, for the summer. Dr. Ed Gent was a metamorphic petrologist. I'll explain metamorphism in a minute. He did his work at Berkeley when Berkeley was kind of a hotbed for this kind of work. And I was very fortunate to work under these 2 guys that summer in the field and to learn about what was behind the mountain building episodes here. So why am I doing this? I really have 3 different reasons. I really want people in the sciences, and especially geology, to see the hand of God, to see the hand of the Creator in the world around them. Number 2, I hope that believers see the depth of the creation that we owe to God and really come to a deeper appreciation of Him. And in that, I think worship springs forth. And finally, I just want to encourage people that God wants us to come into a relationship with Him. Okay, so here's the geology. Paleomagnetism studies have shown that the Earth really has had a history of continental development over many billions of years. So this is theoretical, but there's good data behind it that an ancient continent called Rodinia broke apart. This is the current North American craton. So here's James Bay. So here's where we're from in Michigan. Colorado
wasn't existing yet, I don't believe, at that point. And when it split, it created this major rift system that filled with sediments. So we're going to talk about those sediments. Around my area, Encampment Creek, it's been estimated that there are approximately 15,000 feet of sediments in that area. So here is the piece of the stratigraphic section that we're going to be looking at. Some of the front ranges of the Canadian Rockies involve these groups. To the west, this was the group that we're looking at. These are, they're called Hadrinian sediments, and their age is around 800 to 700 million years ago. They have some unique characteristics. If I can figure out where I put that. These sediments contain Ediacaran fossils that predate the earliest recognized plants and animals. The sediments contain stromatolites, which are ancient communities of cyanobacteria that trap sediment and build up over time. So we worked out some stratigraphy to be able to map. When geologists look at the sediments, they start to, or the metamorphic rocks in this case, they look at what's called the lithology, which has to do with the composition, the minerals that are in the rocks, the granularity, grain size, and then they look at things like foliation and so forth to describe the rocks. So in the area I worked in, we determined that there were really 4 major formations separated by this brown zone that we could map on the ground. And we described them so we could follow them in the field. Turns out years later that although these Hadrinian sediments, which we call the Horse Thief Creek group, were indeed in our area, we didn't have the stratigraphic column exactly right. We thought we were looking at something a little bit younger. Turns out that a very similar sequence that we mapped was a little bit older. So just an example of how geology evolves over time. So this later work was done about 15 years later. So here's the map that we produced from that summer's work. This was my primary area that I was responsible for. There was some very interesting geology to the north that fit into my area, so that's why the map shows both. So we've got green, blue, pink, purple is the order of the stratigraphic sequence that we're mapping. We had an uppermost unit that was full of mica. You'll recognize mica as that platy, either white or black mineral that you sometimes come across if you look at rocks. There was a carbonate unit, which was not very thick. Carbonates come from biological or chemical reactions in seawater. But these blue units, the carbonate units, were very helpful to map structures, like this hook structure up in this area. And then down here, even where you have the sequence, it's a little bit fuzzy, but this is the carbonate unit that helped us to discern what the folding looked like. And then there were a couple of other units in here. I'm going to show a cross-section in a moment from A to B to show you how this fits together. This is the Rocky Mountain Trench, a major geographic feature. And then, I went too far. Then finally, we mapped what's called a metamorphic isograd. This is the appearance of a mineral. I'll show you a picture in a minute, but this is starolite from an area close by. It's a brown mineral that forms very nice crystals. This is blue kyanite. Most of the kyanite that we saw was much finer grained, but we took home that summer a piece that was about 8 inches long. So this is what kyanite and starolite look like. So this line right here represents the incoming of starolite, which means it's a chemical reaction involved across this boundary. And it shows you in the field what the metamorphic conditions were. So isograd equal metamorphic conditions. We were also mapping the fold structures. It's very common in these mountain building metamorphic regions to have multiple phases of folding over time. And in a minute, I'll show that really this whole process took a period of over 125 million years. So in an area just to the south, we see very clearly these F1 folds, which were the oldest, with a schistosity, a layering of minerals going through the hinge. In my area, we saw some folding beginning in the hinges, and these were much more local folds. Turns out that, I'll show it again in a minute, that some of these kinds of folds had amplitudes of over 50 kilometers. And then also in outcrop, we saw this third phase of folding with these crenulated micas in the folds. So here's an example of the regional foliation, we called it, which was parallel in both the F1 and F2 folding episodes. Then here is a nose of an F2 fold with Dave sitting in the nose. So very characteristic of the area. And then finally the crenulation folding of the F3 folds. So when I came back to the desk and started to put the stratigraphy together, it was clear that something was a little bit odd. And we started to look at how the sequence could have been produced. And we realized that we could have been looking at a very, very large fold, but we were only looking at a piece of it. Here's a cross-section of the that I produced. So this was a very large F1 type fold that had been refolded by an F2 phase. That little hook I showed you earlier is this hook here projected down from the north. Okay, let's talk about metamorphic rocks for a minute. Samites are very quartz intensive. Peelites, which I just skipped by, these are aluminum silicate rich rocks, and they're really great to metamorphic petrologists because they produce lots of interesting minerals to study. So here's an example of the starolite. Here's an example of garnets and kyanite. So one of the first things that a petrologist would do is to make thin sections of these rocks and then examine them under a microscope which has polarization, like polarized sunglasses. When you polarize light, it shows a definitive characteristic of the minerals as the light passes through it. So here we have kyanite, and you can start to see the relationships between this foliation and this kyanite. Kyanite here is overgrown in earlier folding phase. In this case, the garnet is being wrapped by the foliation. So you can start to figure out some of the processes that relate the folding episodes to the metamorphic growth of these crystals. So here's one equation that you could use to describe this isograd I was talking about, in which you have garnet and biotite breaking down to produce starolite. So then you can take those kinds of equations and plug them into thermodynamic equilibrium constant equations. So here's an example of that format. So we took a number of different equations from the minerals that we found. We wrote these equations from them. Whoop, I'm doing too far. And when you take the equations here, I'll go back, and these are called Gibbs free energy equations. When you set Gibbs free energy to zero, you're basically saying that everything is in equilibrium, and then you can solve for these equations. So this chart here shows that the variation of composition would suggest that these minerals have achieved equilibrium. So basically you wind up with a straight line, you solve multiple simultaneous equations, and you come up with temperatures and pressures. So we're looking at 600 plus degrees centigrade for the formation of some of these minerals, and 8 to 9 kilobars of pressure.
Later on, some other work by Ed Gent showed that these were pretty reasonable. His estimates were a little bit lower using some other geothermometers and geobarometers. So what we did is we plot these numbers and compare them to experimental curves to make sure that we're in the ballpark. So this was actually from a carbonate geothermometer, and here's my samples here with those temperatures and pressures. So the bottom line is we can tell what's going on in these mountains. And we look at the complexity over the years, over the many millions of years, and we come up with a picture that looks like this. Here's this big nap, here's the refolding. Currently, some geophysical evidence is supportive of this kind of model for this Amanica crystalline belt. It's all there because there was westward movement of the continent. So, what's my bottom line? My bottom line is let's worship God. Come, let's sing for joy to the Lord. Let's shout joyfully to the rock of our salvation. Let's come before His presence with a song of thanksgiving. Let's shout joyfully to Him in song with instruments. For the Lord is a great God and a great King above all gods, in whose hand are the depths of the earth. The peaks of the mountains are also His. The sea is His, for it was He who made it, and His hands formed the dry land. Amen. Yes.
I have a very childish question, but do you mind passing down your rocks?
Okay, so here's a shameless plug. My wife and I have written a book, and in the book I talk about the geology, but this is our testimony. And where the book is, I'll have the samples.
Oh, okay. Good to know.
But since you asked, here they are. Thanks.
Thank you.
So David, have you been able to go back to that area since you did your thesis?
We've traveled across BC and along the Trans-Canada. I've never been back to Mica Creek. Yeah.
And what has the research shown since then?
The research basically confirms what we started to figure out back in the 70s. There's just a lot more detail. The most interesting thing to me is that this large nap structure, which in classical geology, the classical forms of these naps are known from the alpine settings, that we have them here. And I hope that this part of Canada isn't lost in the scientific investigation, that over the years, because there's a lot of great information. I see my major professors retiring, and I'm not sure what's going to happen to all that information. But there's a professor from Carleton University that has encouraged these guys to publish some of their last findings. Yeah. Yes.
This is really a fascinating story of reverse engineering the mountains. And I wonder if you thought about why God created such an evolving planet that's dynamic, the pieces of the planet move. But I guess recently it's been in a very stable kind of situation, which is good for us. But
only the last 10,000 years.
Right.
Yeah. I mean, climate-wise, right? In the Holocene. So I got to refer to Hugh Ross with an answer. Nancy and I, a couple of years ago, picked up his book, Design to the Core. He talks from the astrophysics side of things, how everything had to be just right. All these star clusters, all these galaxies in just the right place for us to be here. I think it's the same answer for geology. Atmosphere development, ocean development, all of those things have to be just right for us to be here. I mean, and I really do view humanity as being the pinnacle of God's creation. So everything had to come before that. Why? I guess someday we'll ask him.
Could I ask
I think we have time for one more question.
Okay, yeah, I was just wondering, when you're talking about this equilibrium thing,
Yeah.
like, what does equilibrium mean? Like, does that mean the mountain's not gonna, like, deteriorate? Like, what does it mean?
I'm talking about the exchange of atoms within a chemical system that is basically cooling down or under pressure and temperature, and these minerals are forming. So those equations are based upon the transfer of different atoms. For example, magnesium and iron in a mineral like starlight, like you have. So we see a composition. So we use an electron microprobe to analyze the mineral oxides. And when we say it's in equilibrium, we can set that equation to 0, and then we can solve for temperature and pressure. If things are not in equilibrium, we couldn't do that. So it's an assumption behind applying that equation. But it seems like a reasonable assumption because over time you've got this mineral and it is stable. You know, and I show that other plot suggesting that the variation is not great, suggesting that, you know, it has achieved equilibrium.